Great. So, yes, you will hear about storylines of heat and drought today and some more. Um, I was a bit in a rush to finish this presentation, so I just screenshotted the nice cover, let's say, that I found online. However, the main issue here is that only my name is listed, but there's also contributions from others. I would say some of the usual suspects. But yeah, just to point that out, it's not all me. Um, Now, what are storylines? I feel like I should briefly define this. Um, in this talk, what I refer to as a storyline is essentially um, some event-specific circulation pattern, and actually also SST patterns um, combined with thermodynamic changes that we just bring together. And by doing so, we can resimulate historic climate and weather extremes and see how much more extreme they turn out or not under additional background warming. And the approach really is not all that new. This has been done before, for example, by Kathleen Verli. And so what I use here is essentially the same framework, but I upgraded the model. This is now a state-of-the-art climate model, CSM2. And I also use, of course, more recent forcing data. Now, for the circulation, I use R5. Um, and for the ocean state, I combine a few different data sets that I would suspect most of you are not familiar with. It doesn't matter too much. What's important to point out here is that in these simulations, I really only enforce the atmospheric circulation pattern so that at a given time, we will have an anticyclone there, but I will not dictate temperature or humidity, and that's important for everything that follows. Otherwise, it wouldn't make any sense. Um, and so, in the different global warming level experiments, a few things are adjusted. Of course, the greenhouse gases and aerosols, but also sea surface temperatures and sea ice. By the way, if that image of the polar bear freaks you out, it's generated by AI, some kind of stock image. So don't feel bad for this polar bear, but maybe you still do feel bad for polar bears in general. Yeah. So that being said, I would like to present, well, the first story or storyline. And that is, of course, one of the, let's say, main case studies of the XAIDA project, this 2021 Pacific Northwest heat wave that I also studied extensively, just like hundreds of other researchers. And to be honest, when I first got these results here, so this is during the peak of the event, when overall we had the most pronounced temperature anomalies. I was maybe I was a bit tired, but it still made me emotional just to see that even such extreme temperatures can there's no roof really, at least for this specific case, no ceiling is what I try to say. So it just gets even hotter. That is, of course, not too surprising in a general sense, but for such an extreme event where we had near 50 degrees Celsius in some locations, it is still a bit starting to see that, yeah, we can't just make things worse even for such a monster event. And you also see this here. I now show you results aggregated for this region that I indicated here, which is a bit of a compromise between where people actually live down here and also where we have the most extreme temperature anomalies. Um, and what you see here is that essentially this scales pretty linearly. So the actual curve in here that corresponds to just the event as simulated by CSM2 during 2021 conditions. And that was a global warming level of about 1.3 degrees Celsius, at least in the model world, but that's close to the actual global warming level. And for 2, 3, and 4 degrees, we see that it does just get worse. And so the scaling here is about 2 degrees more in terms of intensity per additional degree global warming. So maybe you're thinking, okay, why should we care about this? Well, I hope I can convince you that this matters by showing you the following map where we now move on to just the raw temperatures and no longer look at anomalies. Because if I go back, okay, sure, the anomalies here are simply mind-boggling, 20 degrees and Celsius and more. But what arguably matters more, at least for us, is the absolute temperatures. And what I should point out is that the model that I use is, of course, a global model, so this is fairly coarse scale. So we do not expect it to resolve the temperatures properly in cities, for example, or also in regions with complex orography, which is actually up here, where temperatures of up to 50 degrees Celsius were recorded. But what you see here is that even though we don't capture all the fine scale temperature structure, we see that in the model world we have an increase from about 40 degrees to 45 and more. And so probably what this means is that in cities we would exceed 50 degrees Celsius if such an event were to reoccur under much more global warming. And this matters a lot because uh, temperature and mortality are not linearly related. So if we make an event just a few degrees Celsius hotter, we will expect quite a sharp rise in mortality. And you see this here. It's a completely different region, but it doesn't matter too much. You just see that, yeah, it's quite non-linear here for increasing temperatures. What you also see is actually this is from a study that is not out yet, but there is a preprint. And in this study, it's shown that during 2022, the basically hottest conditions were responsible for a substantial amount of the overall mortality across the whole summer. You see that on the right-hand side. That's the percentage of total heat-related mortality in summer caused by a single deadliest week. It's kind of nice that I show you something from 2022 now, because this brings me to my next topic, which is the 2022 European summer. What you see here is now also temperature anomalies, and this is getting a bit boring already, but I promise it will change. You will see more things. It's not going to be as obvious as here. Well, okay, if we resimulate the 2022 European summer, it gets even hotter. Okay, and that's what you see here. What I found interesting is that already at a global warming level of 2 degrees, the 2022 summer would no longer have negative temperature anomalies. So it would just be above average compared to 1980 to 2023 throughout the entire summer. You see that here for the orange line. But what's maybe a bit more relevant in the context also of the topic that the topic of the talk today, as well as just 2022 overall, if you think of it, I think it's more remembered as a very dry summer. And so what you see here now is soil moisture anomalies for the different global warming levels. And I guess as expected, soil moisture anomalies are simply more negative, so soil desiccation is even more pronounced. And why is that? Well, I thought honestly that it was going to be mainly evaporation because it's much warmer. You see that here. So there is just more energy to evaporate water. However, what we actually see is that we have quite a substantial reduction in precipitation. So I move back and forward between precipitation anomalies and raw values here. It's kind of the same thing, really. But what I want to bring your attention to is that for a global warming level of 4 degrees, we tend to not really capture the peaks at all. And so throughout summer, there is just less precipitation. And as a consequence of that, there is also less evaporation during the peak of the event. And what this means is that evaporation actually does not really contribute to the more pronounced soil moisture anomalies that we see. Instead, it is simply the more pronounced precipitation shortages. However, if we go a bit further back in time, we see that in spring, where water limitation generally is not as pronounced as in summer, we do see that here I only show you the most extreme case, global warming level 4 degrees in actual. We do see that there is more evaporation, and so enhanced evaporation still does contribute to the stronger soil desiccation, just not during summer itself, because we are already in a regime where evaporation is very, very water limited. Okay. So far, so good, hopefully. Next comes case 3, and that would be the Amazon 2023 drought. What I show you here is very similar to what I showed before for 2022 in Europe, soil moisture anomalies. But if I just go back a little bit, you will see that unlike for Europe, in the Amazon, we don't really see an intensification. The soils don't really get drier, even though in these model simulations, I have quite a bit more warming present for the orange, red, and dark red lines in here. And I will just have to quickly move, okay, this around. So yes, that to me was quite surprising. So why is that? Isn't there more evaporation? And the answer to that is yes, there generally is a bit more evaporation, but there is also more precipitation. So for example, here, if we compare the dark red line to the blue line, for example, or to pretty much any other line, we see that early on, before the peak of the event, so around June, July, there was just more precipitation in that simulation, and that then led to the soil moisture declining less quickly than in the colder simulations. We also see that later on, the warmer simulations do drop a bit more quickly in terms of soil moisture. There is more evaporation. So evaporation also plays a role for sure. But the interesting thing here is that these are different trajectories. Precipitation does not really change in the same manner. It doesn't really all scale linearly. And so we end up with different trajectories. But interestingly, the lowest point during the peak of the event does not get worse compared to the original simulation. And so that is really the opposite of what I saw for the European drought. So yes, just to summarize this, for now, evaporation tends to increase, but so does precipitation. And so the drought, soil moisture drought here doesn't change too much. I do want to point out that this could be a very nice result, right? If you think about it, oh, okay, if we have the same dynamic, the same dynamics, the same circulation pattern, the same sea surface temperature anomaly patterns also, then this drought does not become worse. However, if we look at projections of JJA precipitation, we see that CSM2 does have a bit of a different pattern in the region that I chose to look at. So right here, we see an increase in this boreal summer precipitation, whereas in the CMIP-6 ensemble, that consists of many Earth system models, of course, we rather see a decrease. So just to recap everything that I've shown so far, um, as expected, if we resimulate a heat wave, for example, 2021 Pacific Northwest event, also 2022 summer, hot just becomes hotter. And the scaling is fairly linear, as has been shown in previous work. For drought, however, it's actually surprisingly interesting in that it doesn't seem to be nearly as linear. For the 2022 European summer, it seems to be, but not for the Amazon. And so this is something that I want to explore further. I now recycle a previous slide because what is actually missing here, in my view, is soil moisture. So if we think about how should we set up these storyline simulations, we have to adjust greenhouse gases and aerosols. Obviously, we have to adjust the sea surf, the ocean state, the ocean surface state. And then give the model some time also so that the warming can really unfold. Should have mentioned that before, but so there is a bit of spin up a couple of years before the events so that the model has time to heat up so that the thermodynamic state can be adjusted properly. But what I don't adjust yet is soil moisture. So the entire long-term soil moisture evolution up until the respective global warming level as of now is essentially neglected. And this is also something that I would like to additionally explore. I don't have those results just yet, but I would like to stick to soil moisture. However, it is a bit of a change of topic, but still related. So I hope that I managed to make it clear that what I do really is I take just the same circulation and I change the thermodynamic state. And so by doing so, I also essentially assume that this is an okay thing to do, that that thermodynamics does not, the thermodynamic state does not really change the dynamics very much. However, there is some research already almost 2 decades ago from Eric. I don't know if he's here, but anyways, he reported in a few papers. I think he published like 3 papers in 2007. Not sure if that's right, but he seemed to be very active. But anyways, he reported that if you run a regional climate model and then decrease the soil moisture, that essentially the anticyclone there becomes more intense. And this is basically what the quote here expresses. And so if you think about this, the soils are to some extent also dry because of the anticyclone itself. But then if we want to understand how such an event would occur in the future, under additional background warming, but we use the same circulation as during present conditions, we might also underestimate how such an event would unfold in the future for otherwise identical conditions. So this is something that has always intrigued me. In all my previous work on heat waves, I could not really look at the effect of soil moisture on circulation itself. What we normally do is we look at the effects of soil moisture for the given circulation, just like in this storyline framework. So yes, what I wanted to address is basically I wanted to see if I can reproduce the results that Eric got almost 2 decades ago, but by doing it with a completely different approach and also not using a regional climate model, but instead a global Earth system model. And this is what I show you next. So This is all a bit cryptic and there is a bit much text on these slides, but essentially the idea that I had is I want to look at heat waves that actually occurred and not just some heat waves that the models come up with. And so first I start with the same simulation as I use for the storylines where I constrain the atmosphere and I force the model to reproduce, let's say, the observed circulation pattern. And I do this right up until the event. Then, when the event starts, I take the soil moisture restart files. That's a bit technical, but essentially, I change the initial state of soil moisture, and I try to do this in hopefully kind of a clever and also fair way. I try to maintain the anomaly pattern. But I just make, in this case, the dry anomalies a bit more dry. That's what you see up here on the right-hand side, as well as I make the dry anomalies less intense. So, and that's what you see here. And what's important is when I then start the simulations again with these different soil moisture states, I no longer constrain the atmosphere. So the model can really realistically, hopefully simulate land atmosphere coupling also with regards to the circulation itself. Finally, I then perturb the atmosphere just a little bit so that I get slightly different trajectories for slightly different initial atmospheric states. But this perturbation is really tiny. Okay, so now before I get to show you some results, just so we're on the same page, when we think of an anticyclone, we should think of something that essentially has convergence aloft and then divergence further below. So the air spirals downwards and spreads out, and this is what you can see here. And that being said, on the left-hand side, you now see for the 2010 mega heat wave geopotential height anomalies. Positive anomalies here means that, well, we have anticyclonic conditions. And you will also see this in a sort of animated version soon, but essentially the jet stream, I hope you can see my cursor, but yeah, the jet stream would be up here, basically where we see white between the blue and red, roughly speaking. On the right-hand side, you see near surface daily maximum temperature anomalies, and you also see our region of interest for which I prepared some time series. And here are the time series. This is quite a lot to take in, but let me briefly guide you through this. So I hope you remember the maps from before. DBD means dry becomes drier. DBW means dry becomes wetter. And there's also original. And you see a few different lines here for the different experiments. And you see temperatures. And not surprisingly, if we make soils drier, the heat wave becomes more intense. If we make them wetter, it becomes less intense. But what we also see is that over time, the geopotential height, which is an indicator of anticyclone intensity, does slowly start to diverge. And we do see, it's not a massive difference, but still we do see that the dry soils are associated with stronger anticyclones. This is not, however, the main driver of the temperature differences. That is really just the surface sensible heat flux and also the deeper atmospheric boundary layers that arise as a consequence of the strengthened surface sensible heat flux, which of course in turn is the consequence of the difference in soil moisture, which I do not show as a time series here. But if I go back, yeah, I hope that you can imagine what it would look like. It's just drier soils for the red lines here compared to the blue ones and also the black. Okay, so the anticyclone becomes more intense. So I find the same thing as Eric. But what wasn't clear to me when I looked at this first is whether this is super trivial, because if we heat the lower troposphere, we expect the geopotential height to increase as a consequence of that. So does the anticyclone really become more intense? And before we look at this, you can now see this anticyclone evolving. You see the winds in zonal and meridional directions here. And essentially, it's a bit easier to see, I think, in terms of the meridional wind. The anticyclone is really here, and the circulation at 500 HPA is clockwise. And yeah, this is what's happening. The anticyclone does, and I haven't mentioned that before, does break down quite a bit sooner in these simulations as compared to when I constrain the atmosphere. But that doesn't stop us from looking at this further. And so now you see a lot of maps that are also not aligned very well, but I will explain what they show. So in the top, you see the geopotential height. And that's the difference between a simulation where I make the soils drier and where I make the soils wetter. And you see first July 31st, always in the left, so the left column, that is right after I start these experiments. So since the color scale is always the same, you don't see much here at all. Actually, you see nothing. But if you move on to August 3rd, you see already that a positive anomaly in geopotential height has started to build. But not only that, we also see that the zonal wind has strengthened a bit, and it has strengthened exactly in the way that we would expect. So yeah, essentially the anticyclone really does become more intense because the winds go northward or poleward quicker here in the dry simulation, and then southward or equatorward also more quickly. That's why the difference here is negative. And so this becomes even more clear as we then progress in time, because this does seem to be a bit of a positive feedback, and so the differences become generally more clear as time passes. So this was just a single event, and I know that it's very dangerous to present results for just a single case study, so I also looked at many other events. However, I was a little overly optimistic with regards to how much I can prepare and also analyze properly. So I'm not going to show you much more. This is already almost it. And I'm going to skip this. The main message of that slide was to say that it was a lot of effort to conduct all these simulations, but that's not so relevant. Let's show, or let's look at something for 2003 instead. So just that you know what the time series are for that are about to be shown, it's this rectangular region here, which I just broadly defined as the heatwave region, and is the same plots that I showed before. Temperatures are higher when the initial state of the soil moisture is lower, as for the 2010 heat wave. What's interesting here is that the anticyclone doesn't break down as fast as for 2010 in my simulations, and so the differences in geopotential height do seem to be a bit more pronounced. And the bottom just also shows the same as before: surface sensible heat flux and atmospheric boundary layer height. I'm not going to repeat that. For yes, I think that's all I wanted to say here. Um, so I know that I just showed you a slide very quickly before where I mentioned four additional heat waves. And so I showed you results also for 2003, but for the other events, actually, I don't seem to find a strong intensification. I want to look at it further, but essentially it's really not super easy to uh, to conduct simulations where drier soils make an anticyclone more intense. So essentially, it's not super trivial. We cannot just make soils drier and expect a strong anticyclone there. And I suspect that what we need is a really persistent anticyclone as well as a stationary one so that this positive feedback can unfold properly. What I also want to mention here is that there's a lot of challenges when it comes to simulating this because, as you can imagine, if there is a positive feedback present, it takes some time to unfold, but also our atmosphere is very chaotic. And in this setup, I then no longer constrain the atmosphere, so the simulations also start to just become chaotic. Let's say at some point they diverge. So it's quite difficult to gauge the strength of this effect properly. It's very timescale dependent and probably also extremely event specific. Um, if some of you read my abstract that I wrote before conducting most of these analyses, I also want to say that the main takeaway message of what you saw here is that, well, there are differences in anticyclone intensity for drier soils, but this is not really substantial. And so, in other words, and a little bit, and it's a bit sad for me because I very much would like to find a stronger signal there, a stronger effect of soil moisture and circulation, but that doesn't really seem to be the case. So, in other words, if we go back to the storylines here, hot gets hotter, and dry probably often gets dry, but not always, at least according to the model that I used. If you go back to that, then this conceptual and also technical separation that we have to use to arrive at these storylines, it seems quite defendable. So in other words, it doesn't seem that the thermodynamics change the dynamics on such a fundamental level, such that we cannot look at these storylines and get somewhat reasonable estimates of what past extremes would look like under additional global warming. And that would be it. Do you have any questions?
Maybe, thank you, Dominik. Maybe to start, there was a question, reflection in the chat from Eric. Maybe you want to read it?
Oh, yes, I did not manage to read the chat well.
It's
Please.
okay, I guess.
Okay. Um, no. So yes, Eric, that's a great question. That was just CSM2 notched with the Era 5 circulation. Yes.
I mean, would be really interested to see how close they are, particularly in temperature. I mean, soil moisture is probably hard to compare, but do you have a feeling on how close we get in temperature?
I mean, initially we are pretty close, but yeah, so the thing is, I plan to run lots of atmospheric initial condition ensembles, a little bit like what you do for the boosting, because I thought maybe I need that. Interestingly, I don't seem to need that at least for 2003 and 2010 because at least initially before the trajectories really diverge, I just consistently see higher anticyclone intensity for the drier soils. Um, but what I also have to say is that 2010 is yeah, only properly simulated in the beginning. The anticyclone um, in reality and also in Era 5 persisted quite a bit longer. So I think it kept being refreshed, if you will, probably by ingesting. Yeah, I think there's different mechanisms. I'm not going to go into that. I'm a bit too tired to try and remember those details. But yes. So to answer your question, initially it's fine, but it doesn't really last too long. It seemed to work better for 2003, but then this might also look very different if I start my simulations one day sooner or later. I also did look at that, didn't make a big difference for 2010. So I did try to choose a suitable initial state to get sort of a long-lasting anticyclone. Didn't quite manage and also didn't want to cherry pick, so I just presented what I did. Yeah.
Thank you. So we still have some time. If any of you have a question, you can just ask or write in the chat. Up to you.
Hi, Dominik. Excellent talk. How model dependent do you think your results are? Have you any feeling? I mean, how well do you know other models' responses to these things?
So I think it depends on the part of the talk. The drought storyline part in the Amazon, that I would definitely expect to be very model dependent, just because I know that the projections of precipitation look different in the majority of the models. But then it's also not super obvious to me yet how closely these things are linked. I resimulated an event that lasted a few months, and I kind of see in the model that it's consistent with the projections, but I don't know if we can generalize this. So I will actually want to do a more systematic analysis where I look at whether we find agreement sort of between the long-term projections and also the changes in, say, precipitation during such a drought event. But that's not clear to me yet. And the other part, for the heat waves, the anticyclone intensity and soil moisture, I can't prove it, but I don't expect this to be very model dependent, just because Eric found it in a completely different model, completely different setup. And it was just really the results seem to be very comparable. Um, but that's my intuition. You have to take it with a grain of salt.
Thanks.
Thank you.
Thank you. So there's another question in the chat. Amir, what about the uncertainty in modeling these events, please?
Yes. So it's a bit difficult to to address this properly, but I think I did have one slide where you could see a little bit that it's not perfect, right? I mean, I use a global climate model or Earth system model that does many things. And so, like I said, I don't expect it to capture the 49 degrees Celsius in Lytton, Canada, which was also due to foehn effects because of complex orography and also in the cities. So there's quite a bit of uncertainty there. But if we look at the larger scales, we know that the models generally reproduce the temperature anomalies very well. This was also shown extensively in earlier work, especially also by Katrin and Valley, whose framework I use and also extend. And so, yeah, I would say that there is uncertainty, plenty of it, but especially for heat, I don't think it's much of an issue if you're interested in the anomalies at larger scales. For precipitation, I really can't give a proper answer at this moment. I think that's a bit more challenging. Thanks for the question. If I dodge the question, please just try again. I don't mean to be a politician here.
Can I ask another question?
Please.
It's really great stuff, Dominik. Have you considered actually for the anticyclone, so the response of the anticyclone also to calculate trajectories like heat budgets along trajectory, like adiabatic and diabatic heating?
Yes, I saved all the data for it. I just didn't manage. I wanted to show so much more actually, but I just didn't manage. But no, I did. Yes, I did have plans for it.
Very good. Is there any other question? Okay, if it's all okay, we can wrap up here. Unless Dominik, you want to add something?
Oh, I'm good.
Okay.
Thanks for attending.
Thank you, everyone. And see you in 2 weeks for the next webinar.